Almost there. You know what? That might be enough. I might be able to get by. As long as I have my pen picked up, it actually isn't too bad because then it doesn't rotate if my pen is selected. This is that picture of the average value that we did before, where the area under the curve, under this blue curve, can be compressed into a rectangle of the same width that you went from A to B. So B minus A is how long that is. And this height up here to, we'll call it C, is the average value. In other words, that's what causes this area that you see here. Basically, if it was like Play-Doh, gets shoved down with your hand and it forces the box to be created. Okay, and that was called, they're going to call it the mean value theorem in this lesson because it's related to the mean value theorem. The mean value was looking for the slope of at a point, or at a, where is it parallel to the tangent line at that point. But I typically call this average value. That way you're thinking of integrals. When I think of mean value theorem, I think of the derivative one. But mean and average are the same word. So a lot of times if they want to use the words mean value, they'll say mean value theorem for integrals, which is what he did here. That we can find a C, f of C, because if I'm going to make that line, that's actually a line, and I'm finding the C value where f of C is at height. Anyway, first problem he did just wanted us to prove that f of b minus, or I mean, from a to b of f of x could be equal to 0. Show that if a function is continuous on AB and on the closed, it's continuous on the closed, it has to be differentiable on the open. In this case, he says, don't cheat. Don't make A equal to B because that's silly. If I go 4 to 4, then what happens is when I do my antiderivative of x squared over 2 from 4 to 4, then we learned already that means top number 16 over 2 minus the bottom number 16 over 2. That gives you 0. So that's cheating. Is there another way that this answer could become 0? And when we find out, then we know that f of x equals to 0 at least once. Okay. Now, what was I thinking of last class? It took me a minute to get my mind wrapped around it. And you could do the same thing with this, or you could even do this, 1 over b minus a, and you could do, it's the same thing. The reason it's the same thing, if you get this part to be 0, then this whole thing, then it doesn't matter what you're multiplying it by, it's still going to be 0. Okay. So what was I thinking of doing? I was thinking of this. If I integrate a to b of f of x dx, that turns into the antiderivative big F of x from a to b, which implies that big F of b minus big F of a. So a very simple question could be asked of you. If this answer has to be 0, what does that imply? Now notice b and a are different numbers, but f of b and f of a turns out to be the same number. And that's why if I subtract, so somehow you're getting, there's a possibility of, here's the one that I'm thinking of. if this is A and this is B, and I want to find the area of the function of a function, I don't know what the function is, such that the answer would be 0 from A to B. That means area under the curve. Well, I'll just extend this a little more. Area under the curve would be, here's a perfectly good function right there on the x-axis. That function is f of x equals to 0. It is a function. It's a horizontal line. Y equals to 0 is a function. It's a horizontal line. And because there's no area under the curve, then that's 1. And look at what he's saying is there's at least one place where f of x has to be 0. Well, there it is. In this case, f of x is 0 all the time. All I needed was at least 1. All right, I've got something else for you. What if the absolute value of f of b is equal to the absolute value of f of a? That would also cause me to have that same problem. I'll give you an example. What if, I'll do my function, a nice pretty function. What if I'm going from A to B? And what if this area under the curve is 4? And the area under this part, which is supposed to be the same picture as that, I could probably do better. Well, not really. I'm not a good artist. I'll try. I'll try to make it look a matching. Wrong color. Close enough. What if that area was a -4? So even though I'm going from A to B, these two parts are canceling each other out. 4 minus 4 gives you 0 because that's what negative area is. Now, granted, the absolute value of 4 is still 4. The absolute value of a -4 is still 4. But because this is above water and this one's below water, they cancel out. So in this particular picture, there's one place on the function where f of x equals to 0. One place. Right here, it's negative. Here, it's positive. He only wanted to show that there could be. He didn't say prove nothing. He didn't say do this heavy-duty math analysis. But I can do one other thing. I think I got ahead of myself. If I'm working with the integral from a to b of f of x dx, and right away, if I'm doing that part equals to 0, he said, if this is true, if that equals to 0, then that must mean my f of b, well, I did that already. I already showed you that would have to be 0. And the only way that can happen is this way, or it can happen this way. There's other ways too. I mean, I could get creative. I could go from A to B and go up. Come on. Up, down, up, down. I could have a lot of places where, just bear with me, that is the same triangle as the bottom. That same is the same triangle as the bottom. So that triangle cancels out the area of that triangle. That triangle cancels out the area of that triangle. You still get area is 0. Well, I should be careful. The area is not really 0 because if you got to go by paint, you still got to buy red paint and blue paint. But the integral of f of x from a to b is 0. The integral is 0. That doesn't mean the true area is 0, because the absolute value of a -4 is still 4. So you still got to buy 4 gallons of paint. I got to buy 4 gallons of paint. Maybe this was smaller. This is 2, and the absolute value of a -2 is still 2. I still got to buy 8, 9, 10, 12 gallons of paint to paint that design, even though the integral was 0. So the area is not really 0. So that's a big deal. He used the average value, and all he did was say, obviously, if that's 0, then 1 minus b minus a times 0 is still 0. It's the same concept. You may not like it. I like my explanation better. I showed you something. All right. And I'm going to try to represent the same idea. This is the function that they gave us in the book. And he wanted to know that a to b of the function is 0. And I'm going to help you out. I'm going to tell you, I'm going to let a be here at 0. And I'm looking at this idea of this integral being area under a curve. So I'm going to zoom in so I can see it here. There's 5 tick marks till I get to 0.5. So this is 1, 2, 3. That's a 0.3. I'm going to key in this function. I already did from last period. The 9x squared minus 16x plus 4. And what this is really good for you is because I'm going to key the function up there for right now. Even though when I graph it, it looks just like the book, or just like what I gave you, okay? Basically, I'm starting out at this x is 0 here. Let's see, that happens right. Oh, there maybe. No, wait. That was the right one. And what I want to do is I want to go to when x is 0.3. So as I slide down, and x is 0.04, 0.1, 0.2. No, I didn't think it went that far. I don't think it crossed there. Maybe it did. I'll go back to my picture. That is 0.3. Okay. So I want to find that area. So with my calculator, you should get this in your head how to do it with the calculator. If you don't have a TI-83 or 84, you have the Inspire. I can't help you with the Inspire because I'm not smart enough to use it. But everybody I know who's picked it up, kids, they pick it up real fast. So second, I don't want to do second, I'm lying. Math, number 9, you see 9 is Fn integrate. So my function, I'm going to go for 0, and I want to go up to 0.3. And instead of typing that function in again, I could just go vars, y vars, and pick the one I've already keyed in. Then I got to say, what am I integrating with respect to? So watch this. This is what we're going to get. Could the answer be there? Before I hit that enter, let me ask you a question here. Could the answer of this be 0? Could the integral, why does it quit writing something? Integral from 0 to 0.3, I'm going to call this f of x because I'm too lazy to write it, of f of x dx. Could this be 0? Anybody? Why not, Andres?
No,
Why
because
not?
there is area.
There's area. What kind of area?
Numeric area.
Oh, jeez. Okay. Can you be more specific? What kind of numeric? Give me one more description. It's above the axis.
Area under the curve?
The area under the curve bounded by this axis right here. That's right.
Yes.
It is, at least we know it's positive, don't we? Positive area?
Yes, sir.
So let me hit the enter key on my calculator. Prove it that I'm right. It is positive, and it isn't 0. It's 0.561. Well, what if I'm trying to find where I got to go to get 0? What if I go a little farther? What if I go to 0.5? Okay, so area. Now I say Mackenzie used under the curve, but it could also be above the curve because the area is always considered to be bounded by the curve and the x-axis. So there's my picture. Almost looks like a triangle. Hey, I think that could be true. If I take the area from 0 to 0.5 of f of x instead of what I did, that could be 0. Could it?
I mean, it would be close, but it looks like the 0.5 one is smaller than.
Why are you raining on my parade?
Oh, sorry.
I was so excited that I had the answer. Okay, tell me your reasoning. You think that you say it's close, but.
Well, because if the per se negative area, just for example, is smaller than the positive, then there'll still be some remaining area left for it not to be 0.
All right. You got me. Oh, wrong page.
It's just us mathematicians, we like to save time, sir.
I know, but man, I was hoping I had it. So you're saying it's close, but no banana is what you're telling me.
Exactly.
Okay, so hit enter. It's still a long way to go, isn't it? 0.375. Well, let's try again. Back to the drawing board. Let's see. What if I get to, anybody want to take a guess? I did 0.5. What if I do 0.6, 0.7? Is that 7? Here's 1, 0.9, 0.8. Here's 0.7. How about that one? Could that do it? Could the integral from 0 to 0.7 of this f of x dx be really close to 0?
Do you want me to be honest, sir?
Yes.
It looks slightly larger, so I have a feeling it will be left over negative.
You are just not much fun. Oh, you're right. Look how close that is. Well, then it's got to be. Did I do 0.6 then? I haven't done 0.6, so let me just do it again with the 0.6 then. It's got to be the 0.6. It's got to be. Ah, man, what happened? It's not quite right. I had negative 0.09, which was like close to negative 0.1. Now I'm back up to 0.1. So it looks like what happened is when I go to 0.7 versus 0.6, this wasn't enough and this was too much. So the answer has to be in here somewhere, right? And answer. Let me try it again. So let me go to, instead of 0.6, which wasn't enough, let me go to 0.66. Let me see. Still not enough. Let me do 0.6. Oh, help if I hit enter first. 0.667.
The closest that I've gotten is 0.666.
Well, yeah, 666. What was you? Because my answer now is negative 0.0008. That's the answer I have on the screen right there.
And then with 0.666, you have 0.0017768888.
What one was that?
0.666.
Okay, so that is at least one x value or two. We're very close, both me and you. We're around the 0.66 something, right? So who said I could stop there? What if I go to the 1? What happens at 1? Let's just see. I mean, I already know it's going to happen at 1 without even being a genius like Hector is. it's going to definitely be a lot more negative area, right? Just to 1, let's see. Oh, no, still negative. Oh, yeah, because it's underneath. It's a lot more negative. All right. Well, back in the picture one more time. Let's see. I could try the 1.5. I could try 1.75 just to see what's happening, and I could try 2. So I'm not going to go back and look at the picture. We've got the 1. I'm going to do the 1.5. That probably still negative. Yeah, I figured that. But now it's coming up. So let me do it again. 1.75. Let's see. 75. We'll get rid of that piece. Still a lot of negative. Let me go one more time to the 2. And then I'm bored. I get bored easy. So now I'll just type in a 2. Last one. Okay, look at that. That 0.000000000000000. I don't know if I got 16 of them. 555. That's 0. Okay, that's a beautiful part. So we found 2 places for sure that we're getting a 0, and I want you to understand why did that happen. We were accumulating positive area. Then I accumulated a whole bunch of negative area. Even when I got out of the 1.5 and I ventured into the 1.75, I was getting closer to the 0. But it's still, these 2 blue regions wasn't enough to make up for all that red. And then once I got to 2, wow, that region really paid off. That region plus that region does compensate for this lower red. Integration is accumulating as you go from left to right. Accumulating. You might be accumulating a positive, you might be accumulating negatives. Then you might be accumulating more positives. That's what you were supposed to get out of this part. And he kind of tells you in the book, he does that picture. He kind of tells you that there are 2 values of C. We found 1. He found 1 by going to the 2. He didn't even bother to tell us. Well, he didn't tell us where the other one was. But we found it. We found it back in about here. We found this value. It's not here. That's not going to give you the area of 0. All that gives you is a function is 0. There are 2 values of the function equal to 0. That is true. Okay. Anyway, well, that's where I want. Oh, I hit that again. This is interesting. This is the whole point of today's lesson. That if you integrate a function with respect to x, and the answer comes out to be another function, we use big F, and that's referred to as the antiderivative. If you wanted to, and you did the derivative with respect to x of your big F, which means big F prime, out pops out small f of x. When you take the derivative with respect to x of the integral f of x dx, the integral cancels out the derivative cancels out the integral, and that's why the answer comes out to just the f. Now, what we're going to look at is the theorem really says that your f of t, and he changed it because he put a variable up here. That same thing we did. We did the exact same thing. We were looking for from 0 to x of some function. Oh, well, we already had function. It was called f of x. I typed it in. But instead of calling it f of x, because there's already x up here, we changed it to f of t. And we use that. The limits are my function of x. this is my function of t. That if this was called y, and remember, there's a number down here, any number, there's the variable up here, and then here's my f of t dt. And if I choose to do y prime, then y prime turns into, when I do the derivative of this side, derivative, out pops out f not of t, but f of x. Because that was the variable I had up here, which was not the same variable as here. That's the basic trick that's happening. I'm going to tell you there's one other thing. That function is with respect to x. So technically, the chain rule would have said I had to have the derivative of this thing here. The derivative of x with respect to x in this particular problem happens to be equal to the 1. So it still comes out to f of x. So let's see if we can use this. This problem would be easy for anybody to do the integral of. Maybe I'll do this one that way. I want to show it to you in action. That if you were to, we're doing y, this is y. If I was to find y, I'm going to integrate from some a just means a number, to x of t cubed plus 1 dt. Almost everybody in this class knows that means t to the 4th divided by 4 plus t from a to x equals to, plug in the x first, x to the 4th over 4 plus x minus, always do minus when you do these two pieces, minus, what am I minusing? I'm plugging in this a, which is just a number, a to the 4th over 4 plus a. So it's not very exciting. I'm going to rewrite it as x to the 4th over 4 plus an x minus a to the 4th over 4 minus an a. A is just a constant. It's not a variable. So he really wants me to do y prime. He really wants to find out what's y prime. I'm doing it the long way, and then I'm going to do the shortcut. So now do the derivative of x to the 4th over 4 plus x minus a to the 4th over 4 minus a, all with respect to x. This will be my y prime, is when I do the derivative of x to the 4th, what did I start out with? Don't I have to take the 4 and bring it to the front? Take 1 away, and then I have my 4 down here. Then the derivative of x is a 1. And here's the hard part, guys. What's the derivative of a to the 4 over 4?
A to the 5th over 20.
Say it again, louder.
A to the 5th over 20.
Okay, it is true, a to the 5th over 20, but what was a to begin with? A constant. So what if it was written as a 2 over 4 to the 4th minus a 2? What would you have said, the derivative of 2 to the 4th over 4, if a was equal to 2? What's the derivative?
4.
Say it again, 4?
Well, 2 to the 4th is 16. Divided by 4 is 4.
Yes, I want, but I, okay, so it's
4x.
but I still want the derivative, not the integral.
So
That would be a
x.
0. Yeah, this turns into 0. This turns into 0. They're just constants. It's a trick question. It's like that one day when I said, what's the derivative with respect to x of pi? You know, I tricked you. It's a 0. It's a constant. So the answer really is 4x cubed over 4 plus 1. Lo and behold, the shortcut says, I don't have to do all this work. Look at this, all this work. I found the antiderivative. I plugged in the upper limit, the lower limit, got an answer, looked ugly. Look at that ugly answer. Then I did the derivative of that answer. And what did I get? The shortcut said that if I am just going from a number, any number at all, to x, the answer will just be x cubed plus 1, which is what I got. Let's see if you were paying attention. Well, it's not really fair because I'll make up one problem. See if we're paying attention. Y is equal to the integral from 2 to x. And remember I said a is any number. So this is just a. This is just a of sine of t dt. Does anybody think they can tell me what y prime is without doing any work?
I know it.
What?
It's sine x.
You're right.
Yes.
You're right. And he saved himself hours of enjoyment. He cheated himself. Now, let's move on. B has an issue. Something is not matching up to the rule. You flip what, Andres?
You can flip it and it'll be the negative version of it.
Yes, is the negative version of 5. The x has to be at the top. The bottom down here can be any number at all. The top has to be what holds the function. And now I'm going 3t sine of t. Now, if I want to do this the long way, good luck, guys. This would be very hard to integrate. Matter of fact, you can't integrate it. You'll never be able to integrate that in this course. You integrate that in Calculus BC or Calculus 2. You integrate this by something called by parts. You treat them as 2 parts, and it's a whole nother world. It's easy, but it's not easy if you've never done it before. So since I can't integrate this anyway, why don't I just, hold on, I'm still doing, that's still y, right? That is still y. I want, what is y prime? Really quick, really quick. Think of what Hector did.
I know it.
Okay, don't let Hector have all the fun. What happens to that x? Where does it go?
In the place of t.
In the place of t. So the shortcut answer is exactly what everyone's saying. I should be writing 3x sine of x. But I'm going to make, if the derivative of x is 1, I don't have to do nothing else. It is times a 1, big deal. But you always got to look at that function and do the derivative of it, because that's the basis of chain rule in reverse. All right, that was a lot of fun. Let's move on here.
Wait, sir.
Yes.
Wouldn't the answer be negative 3x?
Yeah, did I drop it off?
No.
Yeah, I did. I lost
I
it.
thought you were going
right
to.
here. No, you're right. It is negative.
There you go.
Of the whole thing. Well, it wasn't much. It's still the same thing. Yeah, I was thinking there's a plus in there. You're right. I lost my negative. Look at the letter C. What's different about it?
It's square.
Yeah, it's squared. And let me ask you a question. Is the derivative of x squared equal to 1?
No.
So I'm going to have to take into account the derivative of x squared. But the first step is still the same. That when I do y prime, that gets plugged into the t. So y prime will still be cosine of x squared, but I want you to do one more step. what is the derivative with respect to x of x squared? Nobody?
Isn't it?
2x.
Isn't it? 2x?
2x, because here's the deal. T, if you're integrating t, you have to have the derivative of t, which is dt. It is the derivative. It's the, we called it the differential before, but it's 1 dt. So this is going to be with respect to x. So now I'm going to have the derivative of my functional part, which was 2x. Now, this one you probably could have done by hand. You literally could have just first integrated from 1 to x squared of cosine of t dt. That would have given you derivative of what is cosine. That's a negative sine from 1 to x squared. Then you could have plugged in the x squared. That gives you a negative sine of x squared minus a negative sine of 1. Then I take the derivative of that answer, just for fun. Derivative of a negative sine of x squared minus, that's plus sine of 1. And what is the derivative of sine? And remember, this is going to require the chain rule. What's the derivative of sine? Cosine, right? So
Yes.
why do I have a negative in here? I can't remember why I have it. Negative cosine of x squared times the derivative of x squared, 2x. Derivative of sine of 1 is just a constant, so it goes to 0. There wasn't? Is the derivative of what? Oh, you're right. Derivative of cosine. The antiderivative cosine is just a positive, right? Got something in my throat. You're right. So that changes the minus to be what?
It would be because it's the antiderivative, right?
Yeah. So there's no minus here, and that becomes minus. But that doesn't affect it because I'm still doing minus the derivative of a number. So it still turns into a minus of that. And you're right, that's not there. And okay, back down to here. There is no minus here. And I still get a cosine of x to x, or 2x cosine of x squared, I mean, right? Which was the original problem. Except it had t in, because it's the same idea. But who wants to do all that work when Hector could do it in 5 seconds? Here's one that you guys could not do. I don't think you guys could integrate that. Maybe somebody in here could, because it's probably related to arctangent, probably some sort, but a very ugly arctangent. Okay. If you go back and look at your derivatives of arctangent, derivatives of arcsine, derivative of arccosine, the functions that give you those answers, you'll remember that. But let me erase it. I'm going to need more room. And we're not going to waste our time trying to integrate it, because that might be hard. So why be hard? Why don't we just go, oh, wait a minute, I see an error. Not an error, but something's wrong with my limits again.
They're in reverse.
I got to flip them again. 1 plus 3x squared here, and wait, I just did that. 1 plus 3x squared up here, and down here is a 4. Okay. Because you want your function to be at the top and your constants at the bottom. So I'm going to keep the 1 plus 3x squared on top. I'm going to keep the 4 down here. So, and I put my negative because I flipped them. So y prime will be everywhere you see the t, you will plug in the function. That's your first step. And I don't care about this 4, because you found out that, that this problem here, the constants just go away anyway, because the derivative of constants will just go away. So it doesn't matter. It's a 0. So y prime should be 1 over 2 plus e raised to the 2 plus e to the x. Except for one small thing. I still have to multiply it by the derivative of the function that I put on top. What is the derivative of 1 plus 3x squared?
X plus x cubed.
No,
I don't know.
derivative.
Oh, the derivative, not the anti. My bad.
Right,
I got confused.
me too.
It would just be 6x.
6x. You could probably make it look a little better by saying 6x goes on top, 2 plus e to the why did I put a 2 here? It's a 1 anyway, wasn't it? 1 plus 3. No, it was e. I'm sorry. I'm looking at the wrong place. 1 plus e to the 1 plus x squared was right. X. No,
Sir,
1 plus 2x squared.
Sir, it's 1 plus 3x squared.
Okay, I see it now. My eyes just cleared up.
okay. I was gonna say that you were putting like the bottom
Oh
function.
yeah, you're right.
Okay.
You gotta, when you're old, you're allowed to make mistakes because, we're old. And I wanted it down here. What am I doing? 1 plus 3x squared. That'll be a good answer. Well, let's see if we're right on any of these. Who knows? Let's see. Did we get x squared plus 1? Well, we did it twice. We did it the long way.
Yes,
we did it
sir.
the short way. Then here he's doing it sort of a lot of steps. Did we get the negative 3x?
Yes, sir.
Okay, good. And how about number 3? Look at all that work they're doing. Oof. I mean, it pays to study and see what he's doing here. Did we get the same answer?
Yes, sir.
Yep. And the 4th one where I was copying it wrong. Did
Same
we
answer.
get the negative 6x over 2 plus e? Yeah. 1 plus, yes, we did. I hope I didn't lose the negative somewhere. I may have. Anyway, moving on. The second part of the fundamental theorem, you already know it. And they're calling it the evaluation theorem. Don't worry, nobody else is. I mean, it's our book. They reach for the stars on things that people have written about in the past. But you've seen this before. It's just solving a definite integral. That's all it is. And he's going to tell you how to do it, which is weird since we've been doing it for quite some time. At least the last lesson for sure. The last lesson was the definite integral. And we learned this trick because we are really tired of finding areas under a curve using rectangles. Now that gets kind of old real fast, doesn't it? That gets really boring real fast. It's okay if you got nothing else to do, but it gets boring. And then you got the left-handed, right-handed. You got the midpoint. You got, I want just upper sums. No, I just want lower sums. That becomes a pain if all I want is lower sums. That means every rectangle one could be left-handed, one could be right-handed. Could be right-handed, right-handed, left-handed, left-handed, right-handed. Who knows? And then what was worse than that? That the area was equal to the limit as n goes to infinity of the sum as k goes from 0 to n of some a function that we called it a function that had a variable of i's in it. Not variable, but times delta x. That's fun too. I bet some of you are still working on that. okay? But the steps were, I don't know why he's saying now, he says it is important. Yeah, we know it's important. First, find your antiderivative big F. Then calculate your big F of B and minus big F of A. And when you do that, that's equal to the, thank you very much. And this process is much easier than using Riemann sums. Riemann sums was those rectangles, whether there's infinity of them or two of them. It's called Riemann sums. He wants us to practice them. Now, here is the problem. I was looking at the homework problems for these, and all the problems that I do that the author says, here's your examples, here's the reading, good luck at some of the homework problems. So I'm going to have to take these slow and give you some feedback of what's happening. This one, I don't think you'll have a problem. The reason is, inside this cosine function is another function. It's called u. Whatever we call it. The reason we call it u is because it's simple to say, what is u in this problem? X. Then what would du be in this problem? 1 dx. You want to put the 1? Fine. You got to go back and look at the problem. Is there a 1 dx in this problem? Let's see, this is cosine of u. That doesn't have it. This is dx. Is that the same thing as a 1 dx?
Yes.
Yes.
So that means it satisfies the conditions. Now you have permission to take the antiderivative. What's the antiderivative of cosine? We just did it a second ago.
Sine.
Sine of x from 0 to pi. Sine of pi. Stop and pause. Make sure you put minus. Sine of 0. Sine of pi. Pi is where? Pi is all the way here. What's the sine of pi?
0.
0. Minus, what's the sine of 0?
0.
0.
I don't remember this answer. Anyway, 0. We calculate definite integrals using the evaluation theorem rather than taking limits of the sums. Yeah, that's, I hope that answer is 0. B. Oh no, there was another B. That was the problem. I thought that said B. No, that was A. There's the answer. We got it right. Here's where the fun begins. Okay, here goes. First of all, this is the secant of u, tangent of u. So u is x. Du, again, is 1 dx, and there it is. Bingo. Derivative of what is secant tangent?
I think it's secant.
Just the secant. That's right.
Sir.
Secant of x from negative pi over 4 to 0. This causes people some problems, even though we can plug it in real easy. Secant of 0 minus secant of, did it say negative? It certainly did. Negative pi over 4. Okay, this caused a couple problems. First of all, when I look at secant of 0, 0 is over here at 1 comma 0. When I do secant, I don't think of secant. I think of cosine of 0. What is the cosine of 0? Using these two numbers, 1 comma 0.
1.
Louder.
1.
1.
1. And isn't secant the reciprocal of the answer I just got?
Yes.
What's the reciprocal of 1?
1.
1. Got one piece. Minus. Now, secant of a negative pi, that scares people with a negative in front. But let me show you.
Sir, isn't cosine an even function? So that means that it's going to be positive.
Yeah. You like taking my sunshine away? She's right. But she knows it for a much more complicated thing than the average bear. I do it this way. If I do a positive angle, cosine is x over r. X is positive, r is always positive. If I take that same angle and go that way, negative angle, it uses the same x and it uses the same r. We don't care about the negative y. Now, that means you can just pretend that it's the secant. Just like Mackenzie said, it's the same answer as the positive. So you know what the answer is going to be. Don't worry about that negative with cosine, okay? Or secant, they're the same. So secant of pi over 4, okay, here we go. Here's my pi over 4, which is a 1 square root of 2. Well, what is the secant then of this pi over 4? What is, if I say 1 over cosine of pi over 4, what is the cosine of this pi over 4?
Square root of 2.
I think, is that the final answer?
No, I was just guessing.
Well, you're on the right track. Cosine of pi over 4 would be the 1 over square root of 2. But the secant of pi over 4 needs the reciprocal, so just flip that right now. So you are right, that is your final answer of that piece. So 1 minus the square root of 2 should be your answer. And so I'll hit my button. I hit the wrong button. That button. There it is. Okay, now the next one. So there's a lot of stuff going on here. This one, pretty typical. I don't think you need any help with this one at all. Just remember that this is 3/2 and x to the half. And I'm going to break it up into 2 only because things get hairy with a lot of parentheses. And I'm going to write this as 4x to the negative 2. So I come back to the left, add 1 to the power. 1/2 plus 2/2 is 3/2. That becomes 3/2 times the 3/2 that is already there, x to the 3/2 power. And it looks like these, wait, no, I'm sorry. It's not a 3/2 times it. It's divided by the 3/2, which makes it a 2/3, doesn't it? 3/2 times the 2/3, because when you take 3/2 and you divide by it, you're really multiplying by the reciprocal. So this goes away, minus, oh, now it's from 1 to 4, minus, this becomes 4x to the negative 1 divided by negative 1. That goes from 1 to 4, and just me clean this one up. I'll get back to this one in just a second. Plug in the 4 to the 3/2 minus 1 to the 3/2. All of that minus, but there's a minus here. So that minus and that minus x becomes a plus, and that was actually a 4 over x if you want to think about it. So 4, we come back to the left. This is a denominator of a 2, so you're talking about the square root of 4, which is a 2. 2 cubed is 8. 1 to any power is still 1. So there's that. Plus, plug in the 4 over 4 minus 4 over 1. You see what's happening? 7 plus a negative 3. The answer is 4. A lot of steps there. Maybe you could be faster than me. Well, I know you can. Let's see if it's right. Is letter
Okay,
C.
wait, sir.
Oh, what?
So when you separated them,
Yeah.
I'm getting confused with myself. Do we take the derivative of, let's say, or the antiderivative?
Antiderivative.
Okay, it's when x is on the the variable at the little squiggly line thing, right?
Yes. Yeah, that was different.
Oh, okay. It's because I wrote derivative, but I meant to write.
And this is as far as I got. And the bad news is these 2 were the most important ones I wanted to do. But I'll do them with you on Friday. No homework for today except for catch up on your stuff. And don't forget your Khan Academy. See you on Friday.
Thank you, sir. Have a nice day.
Thanks, Hector, for all
Bye,
you
Fred.
do. Bye, Mackenzie. Thanks a lot. Andres, as always, a lot. Too bad they can't hear you. They can't hear you, and you guys sometimes are sharper than some of my sleeping beauties. What? Oh, yeah, sure. Yeah, not a problem. I'm not going anywhere. Oh, you have another class you're supposed to go to? You're supposed to go to first period? Why do my first period kids never show up?
Oh.
No, actually, I think one drives and he sneaks out. I don't know about the other guy. Yeah, no, me too. I would have done it too.
It's that bad. So, like, you don't really do anything when the teacher's here.
Yeah, the people that drive or get picked up can leave early. Like,
They can.
Yeah.
Oh, so he thinks he's being like he thinks he's being deceiving, mischievous or what's the word? Deceitful, or whatever. Yeah, something like that. That's like a monster movie. The Insidious. It's Friday. Well, then if you stay here, Julissa, I can pull up that problem in the My Math Lab and see what they were telling you.
Okay. I need like 3 more questions.
Oh, wow. So let me guess, you aren't paying attention to my lecture. My God. You're just hoping I record this, right? Wow. I've seen everything.